Dear students, welcome to the next lecture of organic chemistry. We have been discussing about the aromaticity of benzene in the last lecture. In this lecture, we shall discuss about the mechanism of aromatic electrophilic substitution reactions. A reaction in which an atom attached to the aromatic system is replaced by an electrophile is called aromatic electrophilic substitution. Usually a hydrogen atom is replaced by the attacking electrophile. Aromatic nitration, halogenation, sulfonation, Friedel-Crafts acylation and alkylation reactions are examples of aromatic electrophilic substitution. The electrophilic substitution reaction can be represented as benzene plus electrophile giving substituted benzene plus H plus. Here the electrophile E plus replaces H plus and forms substituted benzene. In the mechanism, the first step is the generation of electrophile. So from a molecule Ez by heterolytic fission, E plus and Z minus are generated, where E plus is the electrophile. Next step is the attack of the electrophile on the benzene ring, that is the pi system of the benzene ring, to form a pi complex. The pi complex can be represented as this. The pi complex slowly changes to a sigma complex when the E plus accepts a pair of electrons from the benzene ring. Thus the ring becomes non-aromatic. The sigma complex is non-aromatic, but it is stabilized by resonance. The resonance stabilization is shown here. The E plus takes the electron pair from this double bond so that this carbon becomes positive. In the next step, this bond will shift to these two carbons, and we will get a positive charge at carbon number 4. The next step, the bond will shift from carbon 2 and 3 to 3 and 4, and the positive charge is at carbon number 2. The non-aromatic carbocation intermediate can be represented as this. The hybrid structure can be represented as shown here, with the positive charge delocalized across the 5 carbon atoms. In the final step, a proton is removed from this sigma complex when a base attacks this complex and the substituted product is obtained. The nucleophilic base will abstract an H plus from the sigma complex, forming substituted benzene and HZ. This is the general mechanism of aromatic electrophilic substitution reactions. In halogenation, halogen substitutes hydrogen in the benzene ring. If the halogen is chlorine, we get chlorobenzene. If it is bromine, we get bromobenzene. And if it is iodine, we will get iodobenzene. Now let us see the mechanism of halogenation. Here we are taking the example of bromination. The first step is the generation of electrophile. In aromatic electrophilic bromination, Br plus is the electrophile. The molecule Br2 plus FeBr3 gives FeBr4 minus plus Br plus. Thus the electrophile Br plus is generated. In the second step, the electrophile Br plus attacks the benzene ring to form a pi complex which changes to sigma complex, which is a non-aromatic system stabilized by resonance. The resonance structures are shown in the figure, and the hybrid structure is represented as this. In the final step, the base FeBr4 minus abstracts a proton from the sigma complex to give bromobenzene, HBr and FeBr3. Thus, the electrophilic aromatic substitution of benzene with the electrophile Br plus gives bromobenzene. Next is nitration. Benzene, when treated with nitric acid and sulfuric acid, gives nitrobenzene. The first step of the mechanism is the generation of electrophile. Sulfuric acid and nitric acid reacts to give H2NO3 plus and HSO4 minus. H2NO3 plus decomposes to H2O and NO2 plus. In aromatic electrophilic nitration reaction, NO2 plus is the electrophile. Second step is the formation of the arenium ion, in which the electrophile attacks the benzene ring. It first forms a pi complex which changes to resonance stabilized sigma complex. The resonance structures of the sigma carbocation is shown here. And the hybrid structure can be represented like this. In the final step, the base HSO4 minus abstracts a proton from the sigma complex to give nitrobenzene. Thus, in aromatic electrophilic nitration, the electrophile NO2 plus attacks the benzene ring, and finally we get substituted benzene, nitro substituted benzene, that is nitrobenzene.